Hello dear students. In today's class, we will try to understand important aspects about Earth's ionosphere. So in our discussions of the introduction to Earth's atmosphere, we have seen the temperature structure of the Earth's atmosphere, where we have categorized the atmospheric layers into 4 different regions based on the temperature. So during that discussion itself, we have made a mention that the Earth's atmosphere can also be characterized based on the electrical properties such as electron density, conductivity and stuff like that. So in today's class, we will try to see how different is the Earth's ionosphere, what are the physical and chemical processes that will be dominant in the Earth's ionosphere, what is the physical reason for the existence of electrons and ions in the ionosphere, and why should it be called as ionosphere, and so many important things concerning the ionosphere. Now, most importantly, let us say if you want to understand the basic definition of ionosphere, let us say. So, what is ionosphere? Ionosphere can be defined or can be precisely, let us say, given the definition saying that it is the region of Earth's atmosphere where the electrons and ions are present in sufficiently large numbers to be able to influence the radio wave communication. So, Earth's ionosphere, the sole purpose of Earth's ionosphere is that it acts as a reflecting layer allowing propagation of radio wave signals or communication using radio wave signals beyond line of sight. So, what generally happens is, since the Earth is curved, so in this picture what has been shown is that the Earth's ionosphere has the ability to reflect radio waves. So, the ability to reflect a radio wave generally depends on the refractive index of the medium. If there is an incoming incident radiation, the refractive index of the medium will decide whether the wave should be allowed to propagate or the wave should be reflected. So, based on the amount of charge density that exists in the ionosphere, the refractive index can be defined, and similarly another parameter which is called as plasma frequency can be defined, and there will be a matching criteria or condition between the frequency of the ionosphere, that is the plasma frequency, and the frequency of the incident wave. If it matches a particular condition, we will realize that this particular radio wave will be reflected. So, what has been shown in this figure is that, so generally line of sight propagation is the most earliest way to transmit signal from one point to another point. So, what has been seen is that the wavelength, so for achieving line of sight propagation, if you have two let us say two antennas, one is transmitter and another receiver. If you have sufficiently a wave with sufficiently longer wavelength, then probably it may be possible that you can transmit and you can receive this particular signal. But if you want to achieve this communication over a very longer distances, then preferably this method may not work. So, then it has been realized after some in the very beginning that there was communication which was possible beyond line of sight. So, this was using the ionosphere. So, people realized there is a conducting layer in the sky which kind of acts as a mirror and which reflects the incoming radio waves and allows line of propagation of signal or communication beyond the line of sight. So, it may so happen that the generally higher frequency waves travel further before they get reflected. So, ionosphere, so in this lecture we will realize that ionospheric density is not something which is constant in height. So, ionosphere has a density, so when I say density, I mean the number of electrons or ions per unit volume. So, density of the ionosphere in terms of charge concentrations is the number of electrons or ions per unit volume. So, the ionospheric density increases as you go up from the ground, and it will kind of decrease as you go away again towards the higher altitudes. So, the density reaches a maximum of, let's say, at a particular height of, let's say, which is called as F layer, the particular height, the density is 10 to the power of 12 electrons per unit volume. So that means that, so higher frequency waves travel further, I mean they travel towards higher altitudes before they get reflected. So here, so and lower frequency waves will get reflected at much lower altitudes, and higher frequency waves will get reflected at very high altitudes. So this is the basic idea, and very high frequency waves will pass right through the ionosphere. So ionosphere will not be able to influence these very high frequency waves. So essentially, so what is the role of ionosphere is that the role of ionosphere is to reflect radio wave propagation that is happening from the earth, and it will only be able to reflect radio waves up to a certain frequency. Beyond certain frequency, in the higher cutoff region, the ionosphere will not be able to reflect radio waves. Rather, the radio waves will, the ionosphere acts as a transparent layer for the radio waves to escape into the space. So it has been seen that various communication devices or various communication methods have been devised to exploit this reflecting property of the ionosphere. Okay, so again, so the ionosphere is a charged layer of the Earth's atmosphere where enough number of electrons and ions are present to be able to influence the radio wave propagation, right. So that is the basic definition. So in this class, what we will try to do is we will try to understand the various layers of ionosphere. What is the fundamental existence of when was the fundamental existence of ionosphere was realized, and what were the major scientific breakthroughs in this particular area of research and things like that. So we will try to understand how does the ionospheric layers appear, when do they appear, what is the chemical scheme behind the production in these particular regions, and this discussion is mainly going to be focused on the understanding of ionospheric layers and photochemistry. So this figure shows the number of electrons per unit volume, let's say per centimeter cube, and on the y-axis you have the altitude. So as you see from this figure, so the number of electrons will increase as you go up, and it will reach a maximum value at nearly 200 to 250 kilometers, and then again it will decrease. So now the first thing that we want to ask ourselves is that why is the ions, why are the ions and electrons forming? So the main reason is that we have seen in our earlier discussions that the solar electromagnetic spectrum consists of X-rays and ultraviolet, extreme ultraviolet radiation. So these radiations are very much energetic, and they have the ability to ionize. Let's say they have the ability, so if you take a photon, they have the ability to ionize atoms, and they also have the ability to dissociate atoms like that. So this results in the formation of electrons and ions. So basically, so it's the incoming radiation which is coming from the top, from the sun, and we know that this figure goes hand in hand with the density. So you see that the density decreases exponentially with density with height. So this is the height, this is the density. So we know that the density decreases exponentially as you go up, So what you can see is that, so this figure has to be complemented with this figure. So this is the neutral density as a function of height, and this is the ion density. So this figure shows the ion density as a function of height. So one striking feature is that the ion density achieves a maximum at nearly 200 to 250 kilometers, and the neutral densities are maximum at the surface, right. So the main reason for this is that the incoming radiation has its maximum amount of energy or maximum availability of photons is at the top. So when it is not exposed to the atmosphere, the incident energy is the most energetic. As it travels, it encounters more and more number of neutral atoms. So it will keep ionizing it and building up electrons and ion densities. Now as it travels further down, what you will realize is that the number of available species, the number of atoms and molecules that are available for dissociation or ionization increases drastically, and at the same time the number of available photons to cause ionization decreases drastically. So there is a balance which is reached, because so now we have so if you consider the amount of energy will be maximum. Let us say if you consider altitude and energy will be maximum. So energy will decrease like this according to the simple Beer-Lambert's law. So energy, and this will, if this is an exponential decrease, and the number of species will decrease like this. So if you combine these two things, what you will realize, there is a balance which will be reached in middle, and this middle point is generally the layer or the point where there is maximum amount of ionization happening, right. So now we will try to see more details into this idea. Okay. Now, so quick facts, if you talk about the ionospheric phenomena. So ionosphere is ionized upper atmosphere that acts as an interface between the earth and space environment. Ionosphere also is the layer which comes in between. So if you have energetic particles or solar winds which are trying to enter into the Earth's atmosphere, ionosphere is the layer which acts as an interface between the solar plasma and the Earth's atmosphere. And the ionosphere is closely coupled to the thermosphere and magnetosphere. So ionosphere is very much, so the interactions that happen in the ionosphere are very much coupled with both the sides. I mean, with the lower atmosphere as in with the thermosphere on the bottom side, and on the top side it is coupled very closely with the magnetosphere. So ionosphere is typically located between 60 to 100 kilometers. So below 60 kilometers is generally the neutral atmosphere, and above 60 kilometers it is the ionosphere. And the altitude structure, just like we have troposphere, stratosphere, mesosphere and thermosphere, depending on the fluctuation of temperature or variation of temperature with respect to height, depending on similarly depending on the available number of electrons at each height of the ionosphere, it can be categorized into 4 different regions, which are called as D region, E region, F1 region, F2 region. So D region is the ionospheric layer which exists from 55 or 60 kilometers to 100 kilometers, and E region exists from 100 to 150 kilometers, and F1 region exists from 150 to 250 kilometers, and F2 region is the one which exists above 250 kilometers. So above F2, the layer is generally called as the top side of ionosphere, right. So the point is, ionosphere can be categorized, can be classified into 4 different regions: D, E, F1 and F2. So we will discuss how these layers are different. In all these layers, what the common species that exists is just electron and ion. So it's not that in different layers different types of species exist. In all these layers, it's only the electrons and ions. Of course, there will be neutral species. So the entire ionosphere can be considered as plasma. So what kind of plasma is it? Is it a weak plasma? Is it a strong plasma? What is the temperature of this plasma? All these details will be discussed as we go further. So the point is, there are electrons and ions which are present in all these layers, but there is a clear rule why there should be different layers. Why don't we treat the entire ionosphere as a single entity or not categorize into various different layers? Okay. Now, so ionosphere latitude structure. So ionosphere at any given point on the Earth. So any given point has to be defined with respect to latitude, longitude, and these are the main parameters which will define or which will identify any point on the atmosphere, on the Earth, right. So the ionospheric structure varies with latitude. Latitude structure is defined by processes that occur due to solar UV effects, Earth's magnetic field, solar wind, interplanetary magnetic field and geomagnetic storms and interactions. Let us say, for example, if we want to understand more about this, let us say if you consider the Earth, this is the equator. So what I am trying to say is, any point on this Earth has a latitude and longitude. So latitude will vary from 0 to plus minus 90, and longitude will vary from 0 to 360, right. Now, the ionospheric densities the overall structure of the ionosphere, that means having distinctly layers of D, E, F1 and F2. So these 4 different layers, of course, they are distinct in the sense that they have variously clearly defined parameters. How we're going to call it as D layer, E layer, F1 layer, and F2 layer. So they will have, but the variation will be in terms of the number densities will hugely depend on, let's say, on the position. Let's say, for example, the equatorial region receives maximum amount of solar energy. So it's natural to expect that electron densities or the ionization, degree of ionization or the amount of ionization that happens in the equatorial region will be very large. It's natural to expect. Then there are other physical processes which will make electron density available in a different concentration. Then let's say, for example, the other type of variation would be generally daytime the electron densities will be larger and during the night time the electron densities will be smaller. Then at the poles, let's say if you take a point here, the electron densities will also depend not just on the solar radiation spectrum, rather it will also depend on the amount of energetic particles that are trying to precipitate into these regions. That means, so the latitudinal structure of the ionosphere not just depends on the solar electromagnetic spectrum, it also depends on several other parameters such as solar wind, the direction of interplanetary magnetic field and geomagnetic storms, so many things. Okay. So now, so the upper boundary of the ionosphere is the beginning of the plasmasphere, and where generally hydrogen, being the lightest species, will escape into these altitudes and becomes available in the plasmasphere. So this is the basic nature of the continuity equation. We will discuss more on this later. Okay, so ionospheric studies, if you just look into the background, I mean, how does this ionosphere came into existence, or when did people realize that there is an ionosphere which is existing in the sky? So the radiation from the sun, so generally what happens, the radiation from the sun at short wavelength, that is X-rays, ultraviolet and UV, extreme ultraviolet radiation, causes photoionization of atmosphere, resulting in partially ionized region called as the ionosphere. So this is not completely ionized. So there are majority of the species will be neutrals, there will be electrons and there will be ions. The Marconi's demonstration of long distance radio wave communication in 1901 started the studies of the ionosphere. So this was the first time when a long distance communication was achieved between England and Canada, where without any repeaters or without any signal transmitters, propagation of radio waves was achieved. So this started the beginning of the ionosphere. Kennelly and Heaviside independently in 1902 postulated the idea that an ionized atmosphere in the upper altitudes to be able to account for the radio wave transmission. So if the transmission has been achieved, so then they must have wondered why or how this radio wave traveled so far, or because the radio waves have very low wavelength and very high frequency, right? So this was the existence of the reflecting layer was formally kind of postulated in 1902. Larmor in 1924 developed a theory of reflection of radio waves from an ionized region. So if the electromagnetic wave is reflected, what should be the criteria between the electromagnetic wave and the plasma? This theoretical framework was provided by Larmor in 1924. So this came much later. If 1902 was the point of discovery when the ionosphere was found to be existing, and the theoretical background came much later. So Brie and Touvet in 1926 developed a method for probing the ionosphere by measuring the round trip reflected radio waves. So at different points of time, so they could measure what is the time of travel for the electromagnetic wave. Depending on the time, they could calculate the height of this particular reflecting layer, and this height of the reflecting layer, like I said before, will depend on the frequency of the wave. So different frequencies were found to be traveling at different intervals of time, indicating that the criteria for the reflectance was matching at different heights rather at the same height. So all this information was also very important to understand the vertical structure of the ionosphere. So the extent of ionosphere, so how far does it stretch? So there are electrons and ions at all altitudes in the ionosphere, in the atmosphere. It's not that only it stops somewhere. But below about 60 kilometers, the charged particle do not play any important role in determining the chemical and physical properties of the atmosphere. So we don't generally deal, or we don't generally talk about the electron and ion density that exists below 60 kilometers, because they are very, very low in number, and so they will not be able to contribute or participate in any of the physical or chemical processes that may happen. So identification of ionospheric layer is related to the inflection points in the vertical density profile. So this is the density. So just like we have seen in the Earth's atmosphere, the thermal structure. So these were called as the turning points, where the temperature structure, or where the temperature structure changed its path and was behaving in a different way, right? So these are the turning points that we generally call, or we can call these are the points where the slope changes, the sign. So depending on this, so we call this as a layer, this as a layer, this as a layer, like this, right? So this is the troposphere, this is the stratosphere, this is the mesosphere, and this is the thermosphere. So just like that, so the profile does look like a single, let's say Gaussian or something like that, like this. But in this, there are small inflection points which will, so let's say for example, this point that you see, this point that you see, this point that you see, this point. So these 4 points are the ones which will be the boundaries of this particular layer. So if you see, the D layer is ending here, the E layer has the maximum density at this point, okay, and the F layer is the one here that you see, F1 is the one and F2 is the one. So the identification of ionosphere layers is related to the inflection points in the vertical density profile. Okay, so this is the basic idea, that why should you call these layers as the single profile as a layered profile? Why should you name D, E, F1 and F2? Now the most important thing is, let's say if maybe you want to look up some books or resources, why should these layers be called as D, E layer, F1 layer and F2 layer? Why don't they can be called as simply A, B, C, D or whatever, or let's say layer 1, 2, 3, 4. So there must be some reason why the ionospheric layers are named like this, D, E, F1 and F2. Why not anything else, right? So probably you may want to look up some books or resources just to find the answer for this curiosity question. Okay, now what are the numbers pertaining to these different layers? So like I said, there are 4 layers. D layer is the bottommost layer, E layer is the layer in between, F1 and F2 are generally the same layer, F layer, but it is for a reason it is called as F1 and F2. So if for example, if you so here there is one more thing that I have to mention here. So during this density profile is what you generally see during the daytime. So daytime, the solid line that you see is the electron density profile during the daytime, and the dashed line is the one that you see during the night time. And so these 2 figures on the right, on the higher side of electron density, are the ones during the sunspot maximum. Yeah. So okay. Yeah. So the daytime is okay. So during the sunspot maximum, and the dashed curves are the sunspot minima. Actually, yeah. So this is sunspot maxima and day, and similarly, so for this the night one is this one, sunspot minima and during the night time. Okay, sunspot minima. So what you see from, let's say if you want to classify day night variations, daytime the electron densities will be larger, of course, but interestingly during the night time the F2 and F1 will just be called as F layer. Okay, and this is so in the daytime you have the existence of all these layers D, E, F1 and F2, and similarly one more. So this is the day night variation, and if you talk about the solar cycle variation, we have already seen what is a solar cycle and how does it change so many things. So, solar cycle generally solar cycle maxima is the time when you expect more amount of energy from the sun, and as a result during the solar maxima the amount of degree of ionization is also large, as you see here, right. So, this is the main aspect of ionosphere. Now, coming back, so you have 4 different layers D, E, F1 and F2. The altitudes already 60 to 90 kilometers is the D layer, 90 to 140 is the E layer, F1 is 140 to 200 and 200 to 500 or 600 kilometers is the F2 region. So, this is the peak. So, within a layer, so what is the point where maximum amount of electron density can be found is called as the peak, and the pertaining density is generally, so the D layer will have a typical density of 10 to the power of 8 to 10 to the power of 10 per meter cube. So, this is electrons. So, in the ionosphere we always assume that the number of electrons are equal in number to the number of ions. So, the charge concentration is 10 to the power of 8 to 10 to the power of 10 per meter cube electrons / ions. So, E layer will have roughly of the order of 10 to the power of 11 per meter cube, and F1 layer, which will be like 200 kilometers, will have a charge concentration of nearly 10 to the power of 11 to 10 to the power of 12 per meter cube. And F2 layer, the most dense ionospheric layer, will have a charge concentration of nearly 10 to the power of 12 per meter cube. Okay. So, the electron density profile does not look the same at all altitudes. So, there is a clear variation at every altitude. Okay. So, if you look at the diurnal and solar cycle variations, diurnal variations are with the day. During the day, with the time, how does anything change? So, what you will be able to observe is that the electron density is larger during the day and lower during the night. And in general, the densities are larger during solar maximum and they are minimum, they are not minimum, they are lesser during the solar minimum. And D layer and F1 layer will disappear during the night time. So, D layer, that is why you do not see a D layer here. So, D layer will not be there here, right, and F1 layer will not be seen. So, in the daytime, it will be D, E, F1 and F2, and in the night time it will be E and F2, or we generally call it as E layer and F layer. So, the top side of the ionosphere merges into the magnetosphere. So, the top side of ionosphere extends or merges into magnetosphere. Okay. Now, so if you see, so obviously if there incident energy is causing ionization, it should be able to create electrons and ions. But generally what you see at different heights of the ionosphere, the major charge concentrations are, or all heights it is electron of course, but at different heights it will be different ion species which will exist, because this is due to the availability of this particular species for ionization to happen. So, at lower altitudes the major ions are O2 plus and NO plus, O2 plus and NO plus. So, at lower altitudes, this is the one, and near the F2 peak it changes to O plus. So, F2 peak is generally in this region. So, F2 peak is this entire F2 peak is this region, 250 or 300 kilometers, and the top side of the ionosphere is generally hydrogen dominated. So, this is the top side. So, if you go here, so it is also called as the protonosphere or something. Okay. So, what I wanted to say is that as you go vertically up from the ground, the electron density is, the negative charge species is always electrons, but the positive charge species could be O plus, O2 plus, could be O plus, O2 plus, NO plus and H plus. So, this is equal in all of this combined will be equal in number with an electron density. Okay. Right. So, now so for practical purposes the ionosphere can be thought of as quasi neutral, which means that the net charge density is practically 0 in each volume element with enough number of particles. So, if you take the ionosphere as a whole, electron density is equal to the ion density. That means overall charge neutrality, overall charge polarity is neutral. Right. So, the ionosphere is formed by ionization of three main atmospheric constituents: nitrogen, oxygen and atomic oxygen. So, this is, I mean, we already know that these are the primary chemical species that we see in atmosphere. So, these species have to be ionized to be able to release electrons. The primary ionization mechanism is the photoionization of by extreme ultraviolet radiation and X radiation. So, you always remember this, these are the main X rays and extreme ultraviolet rays. So, these are the main wavelengths which will produce maximum amount of energy. So, extreme ultraviolet is 10 to 100 nanometers and X rays probably can be 0.1 to 10 nanometers. Okay. In some areas, the ionization by particle precipitation is also important. That means in the polar region. So, this happens in the polar regions. So, polar regions are the ones which will allow extremely energetic particles to be precipitated into the Earth's atmosphere. So, when these particles come, obviously they have a lot of energy and they will ionize electrons and they will ionize atoms to release electrons. So, in addition to extreme ultraviolet and X radiation, ionization may also happen with extremely energetic particles. The ionization process is followed by a series of chemical reactions which produce other ions. So, it is not just it's not a single step process, rather very lengthy or very long cycles of processes exist for various species to be able to account the observed or seen electron density with respect to height. So, once the electrons and ions are formed, so let us say for example, atomic oxygen releases an electron. So, this happens during the daytime when there is available photon. So, what happens is that, so once they are released, they need not stay as electrons, they need not stay as free electron and ion. So, generally what happens, immediately they will recombine. So, they will recombine and just give you back the oxygen, that is it. So, so during the daytime electron ionization happens, and during this time is electrons and ions are released, and immediately depending on the lifetime of a particular reaction and the concentration of the participating chemical species, they will immediately recombine, giving you back the neutral species. So, this process is called as the recombination. Ionization leads to the formation of recombination. So, ionization or photoionization to be more precise. So, let us say photoionization leads to the formation or existence of ionosphere, and recombination causes the ionospheric electron density to be lost. Okay, so, these two processes are the ones which will control the strength of ionosphere at any given point of time, how much amount of photoionization is happening and how much amount of recombination is happening. So, if they do not balance, you will see that there is still available electron density. So, it is very, I mean, it is a clear example that is very easy to understand. So, if you say that electron density is created by the solar energy, it is of course, then once the day passes and if that particular part of the earth enters into the night side, there is no reason for electrons to be created again, ionization to be happening again. So, that time all the electrons and ions should recombine eventually, leaving you neutral atmosphere, but that does not happen. So, various other things come into picture. We will see how the electron density is retained during the night time as well, not just during the daytime, but also during the night time, right. So, if you look at this, the basic temperature structure of the atmosphere, we have seen this earlier. So, what you see the various layers of atmosphere. So, this is how the temperature structure looks like. So, this combines, so this figure has to be brought closer to understand how the ionospheric regions will be identified or tagged with respect to the neutral species. So, this figure shows the electron density. So, this is the ionosphere, or so on the right side, this yellow curve that you see is the neutral density that is varying with respect to height. So, this is an exponential decay. So, So, this varies similar to pressure or density. So, this is just an exponential of minus h by h, right. So, pressure or density or number of particles per unit volume or number of atoms, neutral atoms per unit volume will vary exponentially, will decrease exponentially as you go up. This is what you see. So, generally, and on the left hand side you have the electron density, which is not exponential in nature, which is a totally different kind of behavior if you compare it with the neutral species. So, what is shown is you see different distinct layers, D layer you see E layer and you see F layer, right. So, this is the basic comparison between the electron densities and the neutral species. So, the electron density of course is clearly different from the neutral densities variation, right. And during the solar maximum and minimum, what will happen is solar minimum will have the neutral species will decay much faster, and at the same time solar maximum will have more amount of ionization available at any given height. So, this is the basic way in which solar cycle variations are induced into the neutral atmosphere as well as in the charged or ionosphere. Okay. And if you consider the day night variations during the daytime, the electron densities are highest and you have the existence of all the D layer, E layer, F1 layer and F2 layer, and during the night time the D layer does not appear, it is only the E layer and F layer, right. So, this is something about the basic structure of the Earth's atmosphere. So, the basic structure of the ionosphere, how does the ionosphere form, what are the salient features of ionosphere, I mean why should this be called as ionosphere and what purpose does it serve, and when was the discovery about ionosphere made and how was the discovery made, and how do you identify various different regions of Earth's ionosphere, things like that. We will continue this discussion with more details about various chemical schemes that are in place in ionosphere to account for the observed or for the available density of charged species in the ionosphere. Okay, yeah.